So in this one, we're going to take a look at Airy's stress function in polar coordinates. Let's review our polar coordinate setup. If we go over x and up y and call this angle theta in this side of the triangle r, then we have the relationships from the Pythagorean theorem that r squared is equal to x squared plus y squared. Or if we want to solve for r, that's equal to x squared plus y squared to the 1/2 power. We have x equal to r cosine theta, y equal to r sine theta. The tangent of theta is equal to y over x, and theta would be the inverse tangent of y over x. All right. Well, let's look at this from the perspective of calculus. From Airy's stress function, we had it expressed as sigma x is equal to second partial of f with respect to y twice. Now, suppose Airy's stress function is a function of r and theta. Well, if we want the partial derivative of f with respect to y, we would take, by our chain rule, partial of f with respect to r, the partial of r with respect to y, plus the partial of f with respect to theta, the partial of theta with respect to y. Well, let's look at some of these terms. Let's look at the partial of r with respect to y. We have our expression for r. From calculus, we take the derivative of that. We'd have 1/2. We're going to have an x squared plus y squared inside of there. Now we're going to have minus 1/2, and then we're going to have a 2 times y. Okay, so the 2 and a half cancel out. We're going to equal to y divided by r. Okay, x squared plus y squared on the bottom to the 1/2 power is r. So it's y over r. Or we can express this as the sine of theta. Now the next thing we want to do is we want to find the partial of theta with respect to y. And for that, let's recall an identity from calculus. The derivative of the inverse tangent of some function is equal to 1 over that argument squared times the derivative of that argument. So the partial of theta with respect to y is going to be equal to, excuse me, we have an expression for theta. It's the inverse tangent of y over x. So it's going to be 1 over 1 plus y squared over x squared times the derivative of that argument, which is 1 over x. We can find a common denominator and multiply things through. That would be equal to x over x squared plus y squared. It's equal to x over r squared, which is equal to x over r divided by r. That's going to be the cosine of theta divided by r. So with that, then the partial of f with respect to y is equal to the partial of f with respect to r sine theta plus the partial of f with respect to theta times cosine theta over r. Alright. Well, now what we can do is we can find the second derivative of f with respect to y twice. Well, the first derivative of f with respect to y is this thing that operates on f. So if we want the second derivative, we take that same thing and operate it on f. So it's the partial with respect to r times sine theta plus the partial with respect to theta times cosine theta over r. So that's going to be our operator. That's one partial with respect to y. And we're going to multiply that by the partial with respect to y. Alright, now we've got some terms to multiply through. Now keep a close watch on me. There are a lot of terms here and I want to make sure I include them all. We're going to have a term that looks like the second partial of f with respect to r twice. And we're going to have a sine squared theta. We're going to have a sine theta times the second partial of f with respect to r and theta times cosine theta over r. We're going to have a term that looks like the partial with respect to theta times cosine theta r over r, operating on the partial of f with respect to r times the sine of theta. Alright, so let's see here. We're going to take this second term multiplied by this first term. Now the cosine theta over r, that's just kind of a constant term there. We're not taking the partial derivative of that. That's multiplied by this operator. But on this first term in the second bracket, we're going to have to distribute that partial with respect to theta on both of those terms. So we're going to have a second partial of f with respect to theta and r times sine theta, and then we're going to have a cosine theta over r. We're going to have the partial with respect partial of f with respect to r, and then we're going to have the partial derivative of sine theta with respect to theta. Derivative of a sine is a cosine. So we'll have this term right in here. Okay, so this multiplication blew this up into two terms. Likewise, I'm going to blow this one up into two terms as well. And I may need to check my other terms too. So I'm going to take this second term and multiply by the second term. I'm going to have the second partial of f with respect to theta okay, we had a cosine theta over r. We have another cosine theta over r. And so I'm taking this one times the second one. Alright, now I'll also have a term that's going to look like a cosine theta over r as a constant out in front. And I'm going to operate on the partial with respect to theta of cosine theta. Derivative of cosine theta is a minus sine. So I'm going to have a minus sine theta over r. So I got those in there. And I think I need to go back and add a couple more terms for these partial derivatives on these first ones. So let me get those in here as well. I'm going to have the partial with respect to r of this term. Well, I don't have an r in the sine theta, so I'm good here. So let me check and let me see if I got all the terms that I need in here. Yeah, I do need one more term. This comes from the partial with respect to r times sine theta that operates on this 1 over r type term. Alright, so let me put a term in here. I'm going to have a partial of f with respect to theta, and I'm going to have a cosine theta. And now I have the partial, and I have a sine theta in there too. And I'm going to have the partial derivative of 1 over r with respect to r, which is going to be a minus 1 over r squared. Let me just check this again. And I do believe I have them all. I do need to indicate this is a second partial derivative here. Alright, so let's see what we have. The second partial of f with respect to y twice then is going to be second partial of f with respect to r twice times sine squared theta plus 2 over r, second partial of f with respect to r and theta, sine theta cosine theta. We have minus 2 over r squared, partial of f with respect to theta, sine theta cosine theta, plus 1 over r, partial of f with respect to r, cosine squared theta, and finally plus 1 over r squared, cosine squared theta, second partial of f with respect to theta twice. Alright, now that's kind of a big mess. We're going to do some simplification here. When theta goes to 0, sigma x will turn into sigma r. So we're going to reduce this down to the case where instead of having sigma x, we're going to turn this into sigma r. If we look at our polar coordinate system, sigma x would be this way, and that's the same thing as sigma r on theta is equal to 0 degrees. So in that case, then sigma r would be equal to, we're going to take theta equals your sine of 0 is 0. We're going to be left with a couple terms. We're going to be left with 1 over r, partial of f with respect to r, plus 1 over r squared, second partial of f with respect to theta twice. Likewise, if we go to pi over 2 radians, sigma x will turn into sigma theta. And in that case, sigma theta reduces down to second partial of f with respect to r twice. Now I'm not going to go through the work, but in a similar way, you can find an expression for tau r theta that looks like minus 1 over r, second partial of f with respect to r and theta, plus 1 over r squared, partial of f with respect to theta, and we can reduce that down even and simplify this as an expression of minus the partial with respect to r of 1 over r, partial of f with respect to theta. So these three relationships will tell us how to find the polar coordinate stresses if we know Airy's stress function in polar coordinates. Now in addition to that, we need to understand what the bi-harmonic equation looks like. And that's actually pretty easy. Easier than what we just did. For plane stress, sigma x plus sigma y is a constant. And sigma z is equal to 0 for plane stress. Well, if we take our stresses and add them up in any coordinate system, the normal stresses, for plane stress, we'll still have a constant. So sigma x plus sigma y is going to be equal to sigma r plus sigma theta. If we add sigma r and sigma theta together in terms of partial derivatives of the area stress function, we have this expression, the second partial of f with respect to r twice, times 1 over r, partial of f with respect to r, plus 1 over r squared, second partial of f with respect to theta twice. Well, what that means then is that del squared f is given by this expression, and if we want del fourth f, the biharmonic, then it would be this same operator operating on del squared f. So we can do that. We'll just write this down. It's the second partial with respect to r twice, plus 1 over r, partial with respect to r, plus 1 over r squared, second partial with respect to theta, and then operating on del squared f, second partial of f with respect to r twice, plus 1 over r, partial of f with respect to r, plus 1 over r squared, second partial of f with respect to theta twice. And if we have f expressed in terms of polar coordinates, del fourth f equals to 0 is combined equilibrium incompatibility. For isotropic materials. Alright, let's leave this as a bite-sized chunk, and then we'll take a look at strains and strain displacements next.